So yesterday, good morning again. Yesterday we were discussing the solution of linear equations. We were looking at three cases. The first case is when the number of equations equal to the number of unknowns, and also we assume that the matrix A is invertible, it's non-singular. So then life is very simple: x equal to A inverse B. But but when you have number of equations lot more than the number of unknowns, which is the case, suppose you're doing some curve fitting. If you have lots of observations and you have to fit some parameters, fit a model to the observations, and the model has some parameters. Usually the observations will be much more in number than the number of parameters. Then you have the situation n is greater than m, because each observation is connected to one equation. So then we have derived this expression, we have done this and shown that x is equal to A transpose A inverse A transpose B. Here again we are assuming that A transpose A is invertible, and your famous regression problem, right, where we try to fit a data line to some data. So, right, so you want to fit a line to some data. So the data outputs is x, this is y. Outputs are, let's say, the data points are given by xi and ti. Okay, and d is like stands for decide. So then the model that we are trying to fit this data with is y equal to mx plus c. So the two unknowns are m and c. So how do we solve this problem? If you approach, take the least squares approach, your error is sigma I di minus yi whole square, which is equal to sigma I di minus m xi minus c whole square. Okay, so this you need to minimize. So therefore, dou E by dou M is equal to 0, and dou E by dou C is equal to 0. So if you take the first equation, you get 2 times sigma I di minus mxi minus c times minus xi is equal to 0. So if you take the unknowns to one side and the knowns to the other side, you get m, so 2 goes away, m times sigma xi square plus c times sigma xi is equal to sigma di xi. So this is one equation. The second equation for dou E by, so this is 1, this is 2. The second equation will be again 2 times sigma I di minus mxi minus c times just minus 1 is equal to 0. So that will give you m times sigma xi plus c times sigma of 1, so that will be capital N. So let's say the number of data points is capital. So here we are using notation small n. Okay, so let's use small n. Small n, Cn is equal to sigma di. So you need to solve this. You need to invert this. That is, you will have a data matrix, a 2 by 2 data matrix times mn gives you, on the output side you will have this and this. So if you invert this, you will get the expressions. Now it will be interesting to show that that expression is same as this expression, and it's slightly complicated, but lots of algebra, but you can show that. Anyway, so that's how you solve the case where the number of equations is greater than the number of unknowns. But if you look at the third case where the number of unknowns is greater than the number of equations, then you will have infinite solutions. So take the simple case where you have right? My constraint is a straight line, and so it can be any point on that straight line. So you'll have infinite solutions. Therefore, to get a unique solution, there you add a constraint, which is minimize the cost function, right? The norm x square. So that will be the closest point to the origin on this straight line. So how do you find that? We have done this using coordinate geometry in your high school, but this is only an example problem. How do you solve the more general case that that comes up in this solution of this equation? So let us do it for this sample problem, because you can get some geometric intuition, and then we'll take up the more general case. So you are trying to minimize this cost function x square plus y square under the constraint ax plus by is equal to c. So if you use a method of Lagrangian multipliers and write down this extended Lagrangian cost function. So E prime is equal to x square plus y square plus lambda into ax minus x plus by minus c. So you take dou E prime by dou x and dou E prime by dou y. You get 2x plus a lambda is equal to 0, 2a plus a b lambda is equal to 0. So you can solve for x equal to, right, minus a lambda by 2 and y equal to minus b lambda by 2. So you get this. And then if you substitute this in this, right, you can solve for lambda. So how do you do that? So there should be a minus sign here, minus a lambda by 2. So then if you substitute it in the third equation, you get lambda. Then plug this back into x and y, you get this. So it's a very simple problem, right? You have done this in your high school. Now let us do the more general case. E x transpose x, because that's a norm square, right? And the constraint is ax minus b, right? Ax minus b is the constraint. But thing is, ax minus b has n equations, because each equation corresponds to one observation. B is of dimension n. So in the original example, that is small case of Lagrangian multipliers that we have seen, we have shown only one constraint. But if you have n constraints, then for every constraint you need to have one Lagrangian multiplier. Okay, so since there are n constraints, you should have n Lagrangian multipliers. So we look at a vector of Lagrangian multipliers consisting of lambda 1, lambda 2, lambda n. We'll call this uppercase lambda. Okay, so therefore your extended Lagrangian cost function becomes E prime is equal to x transpose x minus this uppercase lambda transpose ax minus b. So then you will get this kind of a product, right? A linear sum of all these equations. So now if you do del E, right, with respect to x, you get 2x here and minus. So you know that if you do del of expression like C transpose x, okay, the answer is C, not C transpose. So similarly here you have lambda transpose A times x, right? The derivative of that will be lambda transpose A transpose of the whole thing. Okay, so that will be equal to 0. So x becomes half of lambda transpose A. A transpose, or sorry, A transpose lambda. Okay. Now Ax is equal to B. So if you plug this in here, this equation into this, so you get half of A transpose lambda minus B is equal to 0. So lambda is a vector, right? So it becomes equal to this. If you plug this back into this, right, you get x equal to this. A transpose times A transpose inverse times B. It's very similar to the previous equation. It's just that the previous equation, the A transpose here came after this inverse. Here it comes before the inverse. Okay, so this is the minimum norm solution for the third case of Ax minus B system of equations. Now, few elements of probability, so that completes our discussion of linear algebra. Few elements of probability, and then we are ready to discuss data and data representation and all that stuff. We will start getting into the main topic of data. So let's define probability, which is number of ways an event can occur by total number of possible outcomes. Right, and if you take a die, number of ways one can occur is 1. divided by total number of possible outcomes is 6, so 1 by 6. Now, mutually exclusive events, only one of the events A or B can occur, so which means only 2 events possible. So probability of A plus probability of B is equal to 1. Or we have n events, then sigma right of P AI is equal to 1. And if A and B are not mutually exclusive, then if we use Venn diagrams, set theoretic representations. So let us take, let's say, 2 events. A is on these prime numbers. We are rolling a die. The 2 events are A and B. A is any prime number and B is any even number. Right? So there is some overlap. They are not mutually exclusive. So if I can depict the 2 sets like this, A and B with some overlap intersection, then probability of A and B occurring, that is, A or B occurring, A union B, is given by PA plus BB minus P of A intersection B. It's A and B occurring. Okay, so this probability A and B is also called joint probability. So now the conditional probability, that is probability of A given the knowledge that B has occurred, right? How much is that? So this is also very simple to understand, again using Venn diagrams. So we know that B has already happened. So now what is the probability that A will happen? So you see that part of B is also A, right? So this is the number of different ways that A can occur if B has already occurred. So therefore, probability of A is the ratio of the green space, which is intersection, by the red space, which is event A. So that will be equal to P of the probability of A intersection B by probability of B. Now, if A and B are independent, then probability of A is simply A given B is simply probability of A, right? So that will be just P. So PA here, left side. Therefore, in the case of independent events, the probability of P and B is simply the product of P, A, and B. So this is true only when A and B are independent. Now we'll look at the concept of posterior probability. That is, probability of A given B is equal to probability of, so we have already seen this, A intersection B with PB. Right. Similarly, if you, by symmetry, to take P, probability of B given A, and that will be PA intersection B by PA. So from these two, you can get that PA given B into PB is equal to PB given A into PA, or probability of A given B is equal to B given A times PA by PB. So that's all some basics of this. We'll get into a topic on PDFs, probability distributions, probability density functions. All right, and how to fit them using a data set in order to find the clusters in data set. So we'll see that towards the end of our clustering topic. So that completes our discussion of math preliminaries. Let us now start with the discussion of data. Right. So we'll look at first types of data, one half of this lecture, and then next thing is types of data visualization. How do you visualize data? So to explain types of data, we need to first understand what is data and what does it have, what is there inside the data. So we'll talk about a data set, right? Data set is collection of data objects, right? What we call data is like basically a bunch of data objects. And data object also goes by different names in different domains. Like, if you're looking at a spreadsheet or a database, for example, each row, if you take, for example, your mark list, which you fill in an Excel sheet, all right, each row will have, the first row will have your roll number, second row will be your name, and then, marks in quiz 1, quiz 2, etc., right? So that whole row is a record. So that's the technology from databases and spreadsheet kind of a domain. A point is, if you're presenting data as a point in n-dimensional space, right, you call it a point, is more geometric and mathematical terminology. Vector is also math terminology. Pattern is a word used more in machine learning, neural networks kind of literature. Again, event, case, more computer science. Sample is more from statistics. Observation is more from scientific literature. We talk about experimental observations. Entity is again from computer science. So point is a data object is a data object is a bag of attributes, some properties, right? So it goes by different names. They're not all identical. There's some shades of difference, but it is data object is a bunch of properties or attributes, but they go by different names in different domains. In this course, we'll mainly be working with this type of data, the vector. All right, this is what is most commonly used. We'll this is what we'll use more in this course. So data object is represented by a set of attributes. Attribute is a property or a characteristic of an object. So attributes can be of different kinds. They can be qualitative or quantitative. Qualitative, again, there are two subcategories. Nominal, that is just a name, right? Like pin code, IDs, and eye color, right? Or names. So you cannot do any mathematical operations with it, right? Say pin code, although it's a number, you cannot perform any mathematical operations because you cannot add pin codes, for example. It doesn't make any sense. So there is as good as a symbol. So these are like symbolic. It's a symbolic property. Ordinal is also qualitative, but it is the difference between ordinal and nominal is ordinal has some kind of a ordering, right? Good, better, best. This is a kind of order. Good is less than better, better is less than best. Okay, so beyond that, I cannot put a number on good. If you want, you can put a number in such a way that you can say good is 1, better is 2, like in the way you give numbers to grades, right? You can do that. But intrinsically, they don't come with any numerical value. So here also cannot perform mathematical operations like arithmetic operations like addition, subtraction, and all, right? So you cannot say better minus good is equal to, I don't know, better plus good is equal to best. It doesn't make any sense. So, but it is still, it is possible to give the inequality relationship between these quantities, but you cannot perform any other arithmetic operations. That is ordinal. Quantitative is just numerical, data. So you can give a number to this. Among quantitative, again, you have different categories: discrete, right? Here you can have binary also, even special category, or continuous. Now, characteristics of data sets. Suppose we are looking at only a data object which has only quantitative data. Then it's like a vector, right? So, the moment you have a vector, it has certain important properties like dimensionality. What's the dimension of the vector? So the thing is, when you use data, you do some operations with it. You fit some functions to the data and things like that. So if you fit a function to a vector, you get a multivariate function. And one problem with multivariate functions, right? So I have f of x or f of x1, x2, xn. One problem with that is, so you need a lot of data to need adequate amount of data to fit a function. So if you have n dimensions, then you will end up with requiring lots of data. Let me give an idea of why that is. Suppose your dimension is just 1, right, 1D. So let us say I want data at certain resolution. Let's say for a unit interval, I want 10 data points or 10 samples. Then if it is 1D, I need 10 data points to fit my function fairly accurately. At the same resolution, if I have 2D data, then I'll have 10 by 10 plus 10 points in each dimension, right? If I want to have the same level of resolution, then I'll require 100 points. Similarly, if n equal to, if it's 3D, n becomes 10 cube and so on and so forth. So for d-dimensional data, the amount of data that you will need is 10 power d. So you see that the data requirement under these conditions will increase exponentially with the dimension. And that is called the curse of dimensionality. Having high dimensions is a curse because you will need a lot of data, and in practice you may not get so much data. The data is assumed to be somewhat scarce, right? So if you fit a function to data which is scarce and dimensionality is high, then it's going to be poorly fitted, and that will cause other problems. So this is called the cursor. All this sequence of problems is called the cursor of dimensionality. So the another reason dimensionality is a curse is um, in reality, although the data comes from a high dimensional space, the intrinsic dimensionality of the data may not be that high. So for example, I can think of three-dimensional data where so I have some data, but it can so happen that all these data points roughly lie inside a plane which is embedded in that space, in 3D space. So if that is the case, then why should I use three numbers x, y, z to represent these points? By a proper transformation, I can represent these points using only two numbers. So I have by a transformation, I am able to reduce dimensionality and solve some of the problems that come with high dimensionality. So therefore, whenever you have high dimensional data, right, you tend to apply the so-called dimensionality reduction methods. Right, we look at a couple of such methods: principal component analysis and self-organizing maps. PCA is a linear method, SOM is a nonlinear method, but both give you dimensionality reduction. So another property of vectors, right, is sparsity. That is, certain kinds of real-world data might have the property of sparsity. Only a small fraction of attributes are non-zero. Take, for example, images of characters. Right, let's say I'm developing a system for recognizing characters. This is what you do in something called optical character recognition, OCR. Right, if you take character image, which is a 30 by 30 image, in that only a small number of pixels will have ink, right, and all the other stuff is just background, which is just white, so that's blank pixels, zero. So among 900, maybe only 100 pixels are ones, right, all the rest are zeros. So this is sparse data. So how do you deal with that kind of data? So that's an important property of vectors. Resolution, that is, whenever you have continuous data and if you express that into numbers, right, we have to deal with the concept of resolution. Right, unless resolution is good enough, you might lose data. So you know from sampling theorem that you study in communication information theory, right? If I have a signal, unless I sample it at sufficient ray, right, I won't be able to reconstruct the signal accurately, right? So that's where you get into the issue of resolution. So types of data, again, record data, which is just vector, or graph or network data, ordered data, spatial image and multimedia data. So record data is just vectors, and you have already seen that, you know this. Now graph data is where the data is given in the form of a graph. All right, I'll discuss this one by one. So record data, like I said, is having having like in a spreadsheet, right? Each row is a vector, and that's a record. Then you can call this a data matrix. Sometimes even documents can be represented as vectors. The document is text, right? It's a bunch of words in a sequence. But you can also represent it as a vector approximately, in the sense you take some. So this is a kind of representation you will need, for example, to classify documents. Let us say I want to classify documents into, or let's say newspaper articles, into whether it's a sports article or a politics article or movie article on movies. So I can pick a bunch of words, keywords, right, and then I count the number of occurrences of that word in that document, and I make a vector like this. So based on number of occurrence of various keywords, I can in principle classify the document into whether it is political or sports or film kind of document. So this is one representation which is commonly used for documents. A very similar representation, which is also called market basket data. Obviously, this is not used only for market data, but you can use it for anything, for many different kinds of objects, data objects. Is let us say you go for shopping, you go to let's say grocery store, and grocery store can have, say, let's say 10,000 different items, but you will only buy some 5 different kinds of items. You might buy so much of bread, so much of Coke, so much of milk. Somebody else buys only beer and bread. Somebody else buys beer, Coke, diapers, and milk. right? So out of those 10,000 data objects, you will buy some small number, and each of them you will buy at certain quantity. Okay, so your bill thing is your bills will be of variable sizes. Your number of items in various bills will be different. So I cannot use vectors to represent it just like that. So because vectors, if you want to compare different different customers and what they're purchasing, those vectors should have same dimension. Only then I can compare. So, but if each person buys different number of items, how do I express them into vectors of same dimension? That's where you will make use of this kind of market basket representation. That is, you take the vector of vector of dimension equal to number of total number of items that are sold by that that shop. Then you see which items are bought by a particular customer and how many of them, and you fill those entries with those numbers, and that vector is represents what the person has purchased. So it will be a wasteful representation because lots of them will be zeros, but it's a representation where the dimensionality of different vectors is the same. So you can compare. So that representation, it's very similar to this document data. In document data also you have, a document can have thousands of words, many different words, but I'm only counting the number of occurrences of some important words, the keywords, and we'll be able to construct a vector which is of common dimension across the objects, across different documents. Next, the graph data or network data, examples are internet. You could think of internet as let's take it as a network of documents, network of websites, right? That's a huge graph data. Then signaling networks in biology or chemistry. Okay, that's another example. Or simply a molecule is also a graph, right? A graph of different atoms. Because the data need not just be represented. I mean, how do you represent a molecule as a vector? It's not simple. It's not natural. Right? A graph representation is more natural. Now, this graph operation, machine learning on graphs is becoming more popular these days. A lot of powerful techniques are coming up. If I have time, I'll cover some of those such topics in this. I haven't done it last year, but I'll try to cover it this year because it's becoming very important. So ordered data, that is data with some intrinsic ordering. Right, let's take video data. Right, it's a bunch of images, but those images, it's not just a collection of images. The images have an intrinsic ordering in terms of time. Similarly, time series data, right? Let's say stock values of Infosys every day, right? That's a time series. Or some sunspot activity, right? Every year, right? That's a time series. So there's intrinsic ordering in terms of time. Ordering need not come only due to time. It can be some other ordering also, like molecular sequence data. This is a bunch of bases, right? Nucleotide bases. So that sequence of bases is also here also you have intrinsic ordering. Or just image data, right? Maps and so on. So these are different kinds of data. Then how do you represent data statistically, right? So the basic motivation behind that is, so all these things that we have seen so far, individual data points or data objects. So now we have a bunch of data objects, right? How do you represent that whole collection? And what are some preliminary ways of doing? There are more sophisticated ways. We'll get to that later on the course. But if you have a bunch of numbers, let's say not even vectors, just single numbers, scalars. You have a bunch of such scalars. How do you represent a set of such numbers statistically? So you have so basically people try to look for two things whenever you have a bunch of numbers. One is the central tendency, another is the spread. Okay, and so that is basically in terms that you already know. What is the mean? What is standard deviation? So mean and standard deviation are just one kind of representation of. So mean is just one kind of representation of central tendency, right? And standard deviation is only one kind of representation of the spread. The other ways of capturing the same concepts. So one popular way of capturing these two things is so there are many different statistical parameters which can be used to represent either of them. So some examples are median, max, min, quantiles, outliers, etc., etc. So let us look at them. So first, if you want to represent the central tendency, so there are several measures for that. Most popular one is mean, which is simply given by sigma xi by n. N is the number of samples. So that is the symbol for that is the Greek letter mu. And there's also something called the weighted arithmetic mean, sigma wi xi by sigma wi. And sometimes, so if there are extreme values, so that will mess up your mean value because they could be coming because of noise in the observation process itself. So people tend to identify the extreme values and delete them, remove them from the data set before you compute the mean, right? These are called outliers. So when you do that, you're set to compute what is called the trimmed mean, right? This trimming refers to the deletion of outliers. Then you have the median, which is the middle value. If you sort all, because we're looking at only scalars here, not vectors. If you sort all these numbers in ascending or descending order, then if you now cut this sorted set at the midpoint, that is so that in each set you have only n by 2 values, right? And so that middle value is, if there are odd number of values, then that's a middle value. Otherwise, average of the middle 2 values. That's called the median. Then mode is the value that occurs most frequently. So the problem is if there is only single, so that is if you draw a distribution of the data, the peak of the distribution will be the mode. But the thing is, when you have multiple peaks, then you have multiple modes. So then your distribution set to be, so if there's only single peak, your distribution set to be unimodal. The 2 peaks, it is set to be bimodal. Otherwise, 3 means trimodal, and so on. So then again, your distribution can be symmetric or skewed. So one distribution that you might have been familiar with in your previous classes is a Gaussian. So Gaussian is symmetric over around its mean value or its peak. In this case, the mean and the peak value are the same. That means the mode and the mean are the same, and even the median is also the same. So in a symmetric case, the mean, median, and mode are all three at the same value. But if the peak is shifted to one side or the other, right? So if let's say it's shifted to the left of the center point, so then mode will be the smallest, then the median, and then the mean. If shifted to the other side, then mean will be the smallest, and then the median, and then the mode. You see that median is always between mean and mode. So the first case where mode is less than median is less than mean is called a positively skewed distribution. In the second case, where the mean is less than median is less than mode, is called a negatively skewed distribution. Okay, so like that, you can have several measures of the central tendency. Then how do you measure this spread or dispersion of data? Here there are again several approaches. There's something called quartiles. So that is to express that, let us present the data in some kind of ascending order. We can do the same thing with descending order also. But so the first number then in this ordered form will be the minimum value. The last number will be the maximum value. Now, so let's say it has n values, right? Now, let's say 100 values. Take the 25th point, right? Then 50th point and 75th point and the last point, 100th point. So the 25th point will be called the first quartile or Q1. 50th point will be the second quartile, which is basically the same as median. So we defined it like that, right? Then the 75th point, right, is called the third quartile or Q3, right? And the last point, right, is the max. These are the quartiles, right? So this is basically a percentile idea. The point at the 25 percentile is Q1, 50 percentile is Q2, 75 percentile is Q3. So then you can talk about interquartile range. So where you take the difference between Q3 and Q1, that is IQR, interquartile range. So with this, you can have a representation of the entire data set in terms of 5 numbers. This is one way to represent the entire data set, which to and capture both the central tendency and the spread. So in this 5 number summary, you have mean on one side at one end, then Q1, then median is Q2, then Q3, and max. So these 5 numbers, 1, 2, 3, 4, 5, represent the entire data set, right? Which is of course a bunch of scalars. So then the box plot, right? It's so you can represent these 5 numbers in terms of more pictorially using what is called a box plot. So here the ends of the box are the quartiles, and the medians are marked. Add whiskers and plot outliers individually. So in the, let's say there's a picture here. Yeah, we have it here. So this is a box plot, right? So this is a median value, and this is my Q1. This is Q2, right? Upper quartile. It's also called lower quartile, upper quartile, right? And then draw a rectangle. So around median, and so you see that these two values do not be the same. The difference between lower quartile and median and upper quartile do not be the same, because the data doesn't have to be symmetric data around median. So I draw a box from the lower quartile to upper quartile. At the point where there is median, draw a vertical line. So box is split into 2, not necessarily equal halves. Then from beyond the box all the way to the lower extreme, that is a mean value, draw just a single line. This is not a box. The box ends at lower quartile on the lower side. Similarly, box ends at the upper quartile on the upper side. Beyond that, draw a straight line going all the way to the max value. So this is called a box plot. So in this plot, there is a box with 2 tails, which are called whiskers. Why is it done like that? Why can't I just draw one whole box or one whole line? Why this drama with a box and a line, everything? The idea is to indicate that most of the data is located inside this region, this interval between first quartile, lower quartile, and the third quartile or upper quartile. The amount of data outside is somewhat less. So to show that the meat of data is here, right? You show this part and the other parts somewhat differently, right? So you show this using an area and show the outside parts, outlying parts using a line. Just show that they are thinner. Okay, so this is called a box plot, and the box plot represents this 5 number summary consisting of a minimum, Q1, median, which is Q2, and right, and Q3 and maximum. Okay, so we have seen the two lines outside is called whiskers. Then points outside, even outside this, if they exist, so they're called outliers. Okay. So, and sometimes the endpoints are also denoted by like another line here. And the box plot can be either vertical or horizontal. Now, one particular example, a popular example of the symmetric distribution is normal distribution, also called the Gaussian distribution. Right, and so the mean of this is mu and standard deviation is sigma. So if you look at the area of the curve between the mean, right, and one standard deviation, 1 sigma, it has 68% of the area is inside that region. And if you go up to 2 sigma, it is 95% of the area. If you go to 3 sigma, it has 99.7% of the area. Right, you might have heard of this 3 sigma quality index and all that, right? In the manufacturing world, basically that says that the number of good quality products, that percentage of good quality products is 99.7%. Right, only that 0.3% of them are defective. So that is 3 sigma. Then people also talk about 6 sigma, which is even higher, like only 99.999 something, are all good. Only that small fraction, 1 million or something like that, are defective. So these are the quality standards, right, expressed in terms of sigmas, which refers to this figure basically. So if you want to describe a box plot, represent a box plot for a normal distribution, it looks like this. So median is nothing but mean here for a normal distribution, that is mu. And then your Q1 and Q3 refer to 1 sigma, right? And it refers to 0.67 sigma. Okay, and so this is nothing like a min and a max, because for a continuous distribution, which is idealization, the data will go all the way to plus infinity and minus infinity. So you cannot make minus infinity the first number, right? So the equivalent of min here is Q1 minus 1.5 times IQR. So this is IQR, interquartile range. Okay, and Q1 minus 1.5 times IQR is effectively the mean. Similarly, Q3 plus 1.5 times IQR is effectively the max. So the box plot distribution in this case will be now this number, mean, this number, and this number. Okay, so you can represent data in 3D box plots also. So if you have a bunch of variables that you want to describe, okay, so I'll call this x1, x2, xn. For each variable, I have some data. So this is basically vector data. Then for each variable, I can draw a box plot, which will look like this. Okay, so a bunch of boxes for if you have n variables. And you can also have a 3D box plot to look like a forest basically, right? So which is what is shown here. So for every so this 2D set of variables, and then for every variable you have a box plot. Then, like I said, the central tendency for a Gaussian distribution is standard deviation, right? In general, which is of course the square root of variance. So variance in general for a bunch of data is defined like this. So sigma square is 1 by n times sigma xi minus mu. Mu is the mean square, and which you can expand this and show it is equal to 1 by n times sigma xi square minus mu square. The standard deviation sigma is the square root of variance. Okay, so how do you visually display these basic statistical descriptions? We have seen a box plot, which is a display of 5-number summary. But 5-number summary is still a reduction. I mean, because you are throwing away a lot of information. You might have 1,000 data points, but you are representing the entire data set using only 5 numbers. But can we do better? Can we give more revealing forms of visual representation for the data set? So other kinds are histograms, a quantile plot, and scatter plot, and all that. So let's see a couple of them. So histogram, basically, you might have done this in other courses. But if I have some data, I divide the data into small bins or intervals like this, right? And count the number of data points that are present in each of these bins, right? So ith bin, let us say, has ni data points. So I make a plot of that. So bin number is on the x-axis, and number of data points in that bin is the y-axis. So I get some kind of a distribution, which is an approximation of a continuous distribution, right? Because if I assume that I have infinite number of samples by maintaining the right distribution, then I decrease the bin size, gradually, and then I get a plot as the limit of this, and this plot is histogram. The limit of that limit that this plot tends to, as I decrease the bin size, infinitesimally, right? That is your probability distribution of the data set. Okay, so but if the bin size is a finite number, then what you get is an approximation of the original PDF, and that is the histogram. So histograms obviously tell more than box plots because box plot looks like this, but this is ideal when the data set is unimodal. But what if it is bimodal? The histogram looks like this, and box plot still shows this. Okay, it doesn't convey the concept that at the peak there is actually a scarcity, a sparsity in the data, right? Whereas there are two peaks on either side of the mean. So that property of data is not revealed by the box plot. Histograms obviously are more informative because obviously there are more slots in it, so it's more informative. So that is the reason why pictorial representation, visual representations are very popular in the data analysis, and we look at some really fancy ways of visualization later in the course. Then quantile plot is very simple. We have already seen this. If I represent the data in an order, let's say ascending order, then the minimum value is the first value, and the last value is the max, which is at the end. Then just plot them plot them in this ordered form. So if you do that, let's say the last x value is the last sample, right, that capital N samples. That is, so last one is this. I'll call this 1 on the x-axis, and first value I'll call this 0. So on this interval between 0 and 1, I plot all the data points in the ascending order. So then the value at 0.25 will be Q1, value at 0.5 is median, right, and value at 0.75 is the Q3. So this is called a quartile plot. It's basically a percentile plot of the data. Then a scatter plot is if I have two variables, right, and data point is two-dimensional. Then I want to see how the two variables are related. So very often the two variables may not be possible to simply connect them using a curve. There could be a lot of noise in it, right? But to see the underlying pattern, if any, right, it will be nice to do that using what's called a scatter plot. So basically, plot the data points as individual points in this space, and don't try to connect them. Just a bunch of points and look at this scatter among the data. So that's a scatter plot, right? So let us stop here. Next class we'll look at data visualization. So more fancy ways of visualizing data. Because you know this saying that a picture is worth 1,000 words, right? So instead of describing the data with lots of words, why not describe that using a picture with lots of color and make data look interesting, make data tell a story, right? So that is the whole objective of data visualization. So let us look at it in the next class.